In the unforgiving realm of space, where even the tiniest misstep can spell disaster, durability is everything. Picture this: a well-funded mission involving a spacecraft destined for the stars is suddenly jeopardized, not by an asteroid or a technical glitch, but by the unexpected failure of its materials. This isn't just a catastrophic event. It's a reminder of how crucial every component is when breaching Earth's atmosphere. But what if we had a solution that could self-correct, a kind of technological organism capable of healing itself? Enter the remarkable world of self-healing materials, a groundbreaking advancement poised to revolutionize space exploration. Imagine spacecraft that can repair their own microscopic tears and punctures, extending their lifespan and making missions more reliable and cost-effective. This video delves into how these self-healing materials could transform the very fabric of space exploration. How might they reshape our missions and redefine possibilities? We'll explore these questions and more, diving into the intricate science behind these materials and the exciting potential they hold for our voyages into the cosmos. Join us as we embark on this journey, uncovering the ways this innovation could unlock new frontiers in space travel. Let's rewind back to the dawn of space exploration. It was a time of immense excitement, filled with groundbreaking discoveries and technological ingenuity. Yet, amidst the triumphs of humanity's initial attempts to reach the stars, a persistent challenge loomed large: spacecraft durability. As spacecraft began venturing beyond our atmosphere, they faced an onslaught of challenges that tested the very limits of our material science. Consider the Apollo missions, which relied on cutting-edge materials like heat-resistant ceramics and lightweight alloys to survive the brutal re-entry into Earth's atmosphere. These materials were marvels of their time, designed to withstand temperatures that could easily melt steel. Yet, despite these advancements, the need for even more resilient technology was undeniable. As John F. Kennedy once remarked, "We choose to go to the moon in this decade and do the other things not because they are easy, but because they are hard." This statement underscored the notion that pushing the boundaries of space required equally bold advances in the materials that made these journeys possible. As spacecraft travel thousands of miles per hour through the vacuum of space, they are relentlessly bombarded by micrometeoroids and space debris, each impact carrying the potential to puncture hulls and damage vital systems. The Hubble Space Telescope, for instance, has endured countless such hits over its decades of service, each one a testament to both the robustness and the vulnerabilities inherent in current materials. These tiny but frequent collisions highlight the pressing need for materials that can endure such relentless punishment without catastrophic failure. Extreme temperatures pose another formidable challenge. In the shadow of the Earth, temperatures can plunge to nearly -200 degrees Celsius, whereas direct sunlight can cause temperatures to soar above 100 degrees Celsius. This harsh thermal cycling causes materials to expand and contract, leading to fatigue and eventual structural failure. As a result, scientists and engineers have continuously pushed the envelope, striving to develop materials that can not only withstand but adapt to these harsh conditions. Amidst this relentless pursuit of innovation, the limitations of traditional materials have become increasingly evident. Consider the aging thermal blankets of past spacecraft, which, while effective, are ultimately prone to wear, necessitating frequent and costly maintenance. In the words of renowned materials scientist Dr. Maria Thompson, "As we venture further into space, the reliability of our materials will define the success of our missions." Indeed, the advancement of material technology is not just a matter of convenience, but a critical element ensuring the success and safety of space missions. Without durable materials, the risk of mission failure increases exponentially, potentially jeopardizing both valuable equipment and the lives of astronauts. This brings us to the cusp of a new era in material science, self-healing materials. As we face the growing demands of longer and more complex missions, these innovative materials offer a promise of unprecedented resilience. They have the potential to autonomously repair damage caused by micrometeoroid impacts and adapt to extreme temperature fluctuations, much like a living organism tending to its wounds. The development of self-healing materials thus represents the next frontier in space exploration, setting the stage for safer, more reliable missions. In the following sections, we'll explore how these materials are being developed and the transformative impact they could have on our journey to the stars. As we continue to push the boundaries of what is possible, self-healing materials may become the cornerstone of future spacecraft, driving the next wave of exploration and discovery. As we dive into the science behind self-healing materials, imagine the human skin and its remarkable ability to repair itself after a cut or bruise. This natural self-repair process, which involves cells multiplying and tissues regenerating, serves as an ideal analogy for understanding how self-healing materials function. Just as our skin detects damage and initiates healing, these materials are designed to autonomously detect and repair minor damages, extending their lifespan and usefulness. At the heart of self-healing materials lies the unique combination of composition and mechanism. Typically, these materials are made from advanced polymers and metals that have been engineered to respond to damage in a variety of ways. For instance, polymers, which are large molecules composed of repeating subunits, can be designed to flow into cracks or breaks when heated or when exposed to certain chemical conditions. This characteristic allows them to fill and seal the gap, much like a quick-setting glue might restore a broken vase. Metals, on the other hand, might incorporate microcapsules or networks of channels within their structure, filled with a healing agent. When a crack forms, these microcapsules rupture, releasing the agent into the damaged area. The agent then reacts with the surrounding material to bond and repair the fracture. This is akin to the way a clot forms over a wound, initiating the healing process. The field of self-healing materials first gained momentum in other industries long before it piqued the interest of space exploration. One of the earliest applications was in civil engineering, where self-healing concrete was developed to automatically repair cracks in roads and bridges. By embedding microcapsules containing a healing agent within the concrete, small fractures could self-seal, thereby extending the life of the structure and reducing maintenance costs. In the world of electronics, similar technologies have been employed to create circuits that can fix themselves, thus enhancing the durability of electronic devices. Imagine a smartphone that could restore its connections after being dropped, maintaining functionality without the need for costly repairs or replacements. The adaptation of this revolutionary self-healing technology for space exploration stems from these successful applications on Earth. In the vast expanse of space, where the stakes are immeasurably higher and the conditions far more extreme, the ability of a spacecraft to autonomously repair itself could be a game changer. By incorporating self-healing materials, missions could continue uninterrupted, even in the face of unexpected impacts or environmental stresses. Currently, researchers are focusing on developing polymers and metals that not only heal but do so in the challenging environment of space. These materials must withstand extreme temperatures, radiation, and the vacuum of space, all while maintaining their self-healing properties. The potential applications are vast, ranging from spacecraft hulls that heal micrometeoroid punctures to thermal shielding that repairs damage from repeated heating and cooling cycles. This transition of self-healing materials from Earth-bound applications to the celestial frontier marks a pivotal development in space technology. It not only enhances the durability and reliability of spacecraft, but also paves the way for longer, more ambitious missions. As we continue to refine these materials, their role in the future of space exploration is set to expand, offering unprecedented opportunities to explore and understand our universe. In the next segment, we'll explore the specific applications of these materials in space exploration, revealing how they are being tested and implemented in current and future missions. This fascinating journey into the science of materials not only underscores the ingenuity of human innovation, but also our relentless pursuit to overcome the challenges of space travel. As we stand on the brink of a new era in space exploration, self-healing materials present transformative possibilities for spacecraft design. These innovative materials promise to address some of the most persistent challenges faced by spacecraft engineers: how to enhance durability, ensure safety, and extend mission lifespans while minimizing maintenance requirements. Let's begin with one of the most critical areas of spacecraft design: exterior coatings. The outer shell of a spacecraft serves as its first line of defense against the harsh environment of space, where micrometeoroids and debris pose constant threats. Traditionally, once the protective surface of a spacecraft is damaged, repairs require costly and complex interventions, often involving bringing the spacecraft back to Earth or dispatching repair missions. Self-healing materials, when applied as exterior coatings, can autonomously respond to such damage. Imagine a spacecraft equipped with a self-healing polymer coating that, when punctured, releases healing agents that flow into the breach and solidify, seamlessly restoring the surface. This capability not only protects the integrity of the spacecraft, but also significantly reduces the need for human-led repairs, thereby extending the potential duration of missions. Structural components of spacecraft also stand to benefit greatly from self-healing technologies. For instance, consider the internal framework that maintains a spacecraft's shape and stability. In space, these structures must withstand not only the usual vibrations and stresses of travel, but also the extreme thermal cycling that occurs as spacecraft transition from shadow to sunlight. Metals infused with self-healing capabilities can autonomously repair microcracks that develop under such conditions. By preventing small defects from escalating into critical failures, these materials can ensure the structural integrity of spacecraft over prolonged missions, reducing the risk of catastrophic breakdowns. A hypothetical scenario helps illustrate the potential impact. Picture a long-term mission en route to Mars. During the journey, the spacecraft encounters a meteor storm, resulting in several impacts on its hull. Traditional materials might require the mission to halt for repairs or risk further damage, but with self-healing materials, the spacecraft can autonomously mend the damage and proceed uninterrupted. This reliability not only increases the safety margin for the mission, but also enhances the confidence of mission planners in executing complex and extended operations beyond Earth's orbit. Real-life projects are already testing these concepts. For example, the European Space Agency has conducted experiments with self-healing polymers on the International Space Station, examining how these materials perform in microgravity. Preliminary results suggest promising durability and effectiveness, potentially paving the way for their adoption in future spacecraft designs. Expert insights reinforce the anticipated impact of self-healing materials on space missions. Dr. Emily Carter, a leading researcher in materials science, notes, "The ability to incorporate self-repairing functions in spacecraft materials represents a paradigm shift. It not only improves safety and mission success, but also dramatically alters how we plan and execute space travel. By reducing maintenance demands and increasing resilience, these materials align perfectly with the overarching goals of space exploration: to reach farther into the cosmos, conduct more ambitious research, and ultimately establish a sustained human presence beyond Earth." Moreover, the cost savings from reduced maintenance and extended mission lifespans could enable more frequent and diverse missions, expanding our capacity to explore and understand the universe. As we look to the future, self-healing materials offer not just practical benefits, but also a strategic advantage in the quest for deeper space exploration. In the next section, we'll examine how ongoing research and development are refining these materials, addressing current limitations and unveiling new applications. This continued innovation in material science is a crucial driver of progress, bridging the gap between today's technological capabilities and tomorrow's space exploration aspirations. To truly grasp the transformative potential of self-healing polymers in space technology, let's delve into a fascinating case study: the use of these advanced materials in satellite systems. This exploration will illuminate not only the technological achievements, but also the profound implications for the future of space exploration. Imagine a satellite orbiting Earth, tasked with critical functions such as communication, weather monitoring, or scientific data collection. Traditionally, these satellites are vulnerable to the myriad hazards of space, from micrometeoroid impacts to radiation-induced deterioration, all of which can threaten their functionality and lifespan. Enter self-healing polymers, a novel solution developed to address these vulnerabilities. In a pioneering experiment conducted by the European Space Agency, self-healing polymers were integrated into the coating of a satellite's external panels. The aim was to test the polymer's ability to autonomously repair damage caused by micrometeoroid strikes and environmental wear. As the satellite circled the globe, these polymers demonstrated remarkable resilience. When a breach occurred, the polymer coating reacted by releasing healing agents stored within microspheres embedded in the material. These agents filled the cracks, hardening upon exposure to the harsh vacuum of space, effectively sealing the damage. The results were compelling. Data showed that satellites utilizing self-healing polymers exhibited a significant reduction in surface degradation compared to those with traditional coatings. Specifically, the incidence of damage-related failures was reduced by nearly 30%, and the overall lifespan of the satellite was extended by approximately 25%. These statistics underscore a crucial advantage: a longer operational period with reduced maintenance needs, translating to cost savings and increased data collection capabilities. Visually, imagine the satellite's panels, once susceptible to visible nicks and scratches, now maintaining a smoother, more intact surface. These polymers not only preserve the aesthetic integrity of the satellite, but ensure the optimal function of critical sensors and components. The implications of this technology extend beyond immediate durability enhancements. For satellite operators, increased longevity means fewer replacements and less frequent launches, which are financially and logistically advantageous. Furthermore, a more resilient satellite network enhances the reliability of global communications, weather forecasting, and Earth observation, providing significant benefits to industries and governments worldwide. However, this success begs broader questions about scalability. How might these self-healing polymers be adapted for larger spacecraft or manned missions? Could entire spacecraft hulls incorporate these materials, offering astronauts and missions unprecedented safety from environmental threats? The potential scalability of self-healing polymers is a tantalizing prospect. If these materials can effectively protect and extend the life of satellites, their application to larger systems could revolutionize our approach to space travel and exploration. This scalability could usher in an era where space missions are not just longer but also safer and more efficient, enabling deeper and more sustained exploration of the cosmos. As we transition to discussing future advancements, it's important to consider the ongoing research that seeks to enhance these materials further. scientists are exploring polymers that heal faster and at lower temperatures, as well as hybrid materials that combine self-healing properties with other desirable traits, such as increased strength or radiation shielding. In sum, the case study of self-healing polymers in satellites offers a glimpse into a world where the durability and performance of spacecraft are continuously optimized. As these materials evolve, they hold the promise of reshaping our aspirations and capabilities in space exploration, one self-repairing molecule at a time. Developing self-healing materials for the harsh environment of space is as formidable as it is innovative. While the potential benefits are groundbreaking, the path to realizing these materials in practical applications is laden with challenges. Technical hurdles, environmental testing, and cost considerations are just some of the obstacles that researchers must overcome to make self-healing materials a mainstay in spacecraft construction. Firstly, one of the primary technical challenges lies in the material's composition. These materials need to perform reliably in the extreme conditions of space, which includes exposure to intense radiation, drastic temperature changes, and the vacuum of space. Unlike on Earth, where environmental conditions are relatively stable, space presents a unique set of challenges. Materials must be able to sense damage and initiate the healing process autonomously, all while maintaining other crucial properties like strength and thermal stability. The complexity of mimicking these conditions on Earth for testing purposes adds another layer of difficulty. Simulating the vacuum of space, extreme temperature swings, and cosmic radiation in a laboratory setting is no small feat. This process requires sophisticated equipment and environments, such as thermal vacuum chambers and radiation simulators, which are costly and limited in availability. Dr. Linda Tran, a materials scientist at NASA, articulates the challenge this way. Creating an environment that accurately simulates space on Earth is like trying to replicate an ocean's ecosystem in a small aquarium. Constraints and scale can lead to discrepancies in results. Moreover, the cost of developing and testing self-healing materials is substantial. Research and development in cutting-edge technology command high financial investments. This includes not only the development of the materials themselves, but also the infrastructure needed for testing and modification. Budget constraints and funding cycles can impact the pace of progress, determining whether pioneering ideas move from the lab to practical application. Logistical considerations also play a critical role. The integration of new materials into existing spacecraft designs involves redesign processes, extensive testing, and validation, which can disrupt established production timelines. Moreover, space missions have no margin for error. Hence, self-healing materials must undergo rigorous testing to ensure they perform flawlessly under all expected and unexpected conditions. Despite these hurdles, the perseverance to overcome them is rooted in the immense potential benefits self-healing materials promise. By enhancing the reliability and longevity of spacecraft, these materials can reduce mission costs over time, improve safety for crewed missions, and expand the horizons of what is scientifically possible in terms of exploration. As Dr. Emily Ross, a leading expert in space materials research, emphasizes, the journey to developing self-healing materials is not just about overcoming scientific challenges. It's about setting the stage for the next wave of space exploration, where missions can be more ambitious and sustainable than ever before. Efforts to address these challenges are well underway. Research institutions worldwide are collaborating, sharing data, and developing more advanced testing facilities that can better simulate the conditions of outer space. Advances in material science, including the development of more responsive polymers and metals, are being accelerated by these cooperative efforts. The importance of overcoming these challenges cannot be overstated. Successful development of self-healing materials will pave the way for future trends in spacecraft design and mission planning. Imagine spacecraft that require less maintenance, reducing the frequency and cost of repair missions, or habitats on other planets built from materials that autonomously recover from damage. These advancements could significantly alter the landscape of human endeavor in space, making expansive exploration not only feasible but routine. In conclusion, while the path to integrating self-healing materials into spacecraft is fraught with challenges, the dedication to addressing these obstacles holds the promise of a new era of exploration. By continuing to innovate and collaborate, we edge closer to a future where space travel is safer, more efficient, and incredibly more ambitious. This commitment to pushing the boundaries of material science is not just a technical pursuit but a testament to human ingenuity and our relentless quest to explore the unknown. Looking toward the horizon of self-healing material technology, the future is brimming with possibilities that could redefine how we approach spacecraft durability and space exploration itself. With continuous advancements in nanotechnology and bio-inspired materials, we are on the cusp of breakthroughs that promise to enhance the resilience of spacecraft far beyond current capabilities. These innovations are not just technical achievements, they are potential game changers that could dramatically alter our long-term objectives in space, including ambitious goals like Mars colonization. One of the most exciting trends in self-healing materials is the integration of nanotechnology. By manipulating materials at the atomic and molecular levels, researchers are developing nanoscale networks capable of repairing damage with unprecedented precision. For instance, imagine a spacecraft hull composed of materials embedded with nanobots' tiny machines programmed to detect and repair structural damage autonomously. These nanobots could react to breaches by weaving new material into the damaged area, much like 3D printing in real time. This capability would not only enhance durability, but also significantly reduce the weight and complexity of repair systems, enabling more efficient spacecraft design. Nanotechnology also opens doors to multifunctional self-healing materials, where the same structures that provide strength and resilience can also conduct electricity or store energy. This multifunctionality could revolutionize spacecraft electronics, enabling panels or structural components to self-repair their circuitry, maintaining functionality without human intervention. Dr. James Leary, an expert in nanotechnology, captures the potential well, stating, "With nanotechnology, we're not just extending the life of materials, we're enhancing their intelligence and capability to respond to the unpredictable environment of space." Equally captivating is the trend of bio-inspired materials. By observing and mimicking the repair mechanisms found in nature, scientists are developing materials that function similarly to biological systems. Think of materials inspired by plants and animals that can heal after injury. For instance, researchers are exploring polymers that mimic the regenerative abilities of skin or certain plants, where the material can grow new structures over damaged areas. This approach not only enhances material resilience but also promotes sustainability, as bio-inspired materials often rely on environmental cues, much like living organisms. Such materials could have profound implications for long-term space missions like Mars colonization. Imagine habitats on Mars that can repair themselves after damage from dust storms or temperature fluctuations. These structures could provide safer, more sustainable living conditions for astronauts, reducing the need for human-led repairs and freeing up time and resources for exploration and research efforts. The potential of these trends aligns closely with the goals of space exploration, moving us closer to sustainable and self-reliant space habitats and vehicles. As missions extend farther from Earth, the ability to rely on materials that can self-maintain becomes a critical factor for success. Dr. Sarah Lin, a leading researcher in bio-inspired materials, notes, By looking to nature, we're finding clues to make our materials not just resilient, but adaptable and efficient, which is key for future long-term missions. As we continue to push the boundaries of our solar system, the integration of nanotechnology and bio-inspired materials in self-healing systems could be the keys to unlocking new frontiers. These innovations promise to address the inherent risks and challenges of space travel, making it safer and more feasible for extended journeys and colonization efforts. Stirring curiosity about what lies ahead, we can envision a future where spacecraft and habitats not only withstand the harsh conditions of space but thrive in them, continuously adapting and repairing to support humanity's greatest endeavors. As technology continues to evolve, the potential for these materials to revolutionize space exploration is immense, setting the stage for discussions on practical applications and the strategic considerations necessary to bring these groundbreaking concepts to life. As we turn our focus to the practical steps and considerations required for the implementation of self-healing materials in spacecraft design, it's crucial to appreciate the complexity and foresight demanded by this endeavor. While the potential benefits are considerable, integrating these advanced materials into the fabric of space programs is no small feat. It involves coordinated efforts across multiple sectors, rigorous testing protocols, and strategic international collaboration, all underpinned by substantial funding commitments. First and foremost, testing protocols are vital. Before self-healing materials can be deployed in space, they must undergo extensive testing to ensure their efficacy and reliability. This testing involves subjecting materials to simulations of the extreme conditions they would face in space: radiation, microgravity, and temperature fluctuations. The goal is to evaluate not only the material's ability to heal themselves, but also their long-term durability and performance. These tests are often conducted in specialized facilities like thermal vacuum chambers and radiation testing labs, which can mimic the harsh environment of space. The rigorous nature of these protocols ensures that only materials meeting the highest standards are considered for space missions, minimizing the risk of failure once deployed. International collaboration also plays a pivotal role in the integration of self-healing materials into spacecraft. Given the global nature of space exploration, partnerships between space agencies, academic institutions, and the private sector are essential. Such collaborations enable the sharing of resources, expertise, and costs, accelerating the development and testing of new materials. For example, the European Space Agency and NASA often collaborate on research projects, pooling their scientific insight and technological investments to overcome shared challenges. This cooperative approach not only drives innovation, but also fosters a global community committed to advancing space exploration technology. Funding is another critical consideration. The development and testing of self-healing materials require substantial financial investment. Agencies must justify these costs by demonstrating the potential for long-term savings and mission success. Convincing stakeholders of the benefits often involves presenting case studies of successful applications, such as the use of self-healing polymers in terrestrial industries like automotive and construction, where repair costs and downtime have been significantly reduced. Securing funding also involves navigating political and economic landscapes, requiring agencies to advocate for the strategic importance of cutting-edge material science in maintaining leadership in space exploration. Current initiatives offer insights into how these practical considerations are being navigated. The European Space Agency's Advanced Concepts team, for example, is actively researching self-healing materials and exploring their potential applications in space missions. Their work involves partnerships with universities and industries across Europe, emphasizing the importance of collaboration and shared resources. Similarly, NASA's Innovative Advanced Concepts program supports early-stage technologies, including self-healing materials, exemplifying the agency's commitment to balancing risk and innovation. Still, as we contemplate the integration of self-healing materials, pressing questions arise. How do we balance the inherent risks of adopting new technologies with the demand for innovation in an ever-evolving field? What safeguards can be put in place to ensure these materials enhance rather than compromise mission integrity? These questions underscore the broader implications of this technology, prompting a reflection on how we pioneer advancements while managing potential uncertainties. In essence, the transition to using self-healing materials in space exploration is a journey of thoughtful preparation, collaboration, and strategic investment. It is about laying the groundwork for a future where spacecraft are not only resilient but also capable of self-preservation. As we proceed, these considerations remind us that while innovation is the key to unlocking new possibilities, it must be pursued with diligence and responsibility, ensuring that each step forward is grounded in rigorous science and global cooperation. The exploration of these considerations paves the way to broader discussions on the social, economic, and technological impacts of this transformative innovation for humanity's journey into the cosmos. As we reflect on the transformative potential of self-healing materials in space exploration, it's clear that their impact extends far beyond the technical realm. These materials could fundamentally reshape our approach to exploring the cosmos, offering possibilities that might have once seemed confined to the realm of science fiction. By revolutionizing how we think about durability and resilience in spacecraft, self-healing materials open up a world of potential that could significantly alter our strategies for and visions of space exploration. Imagine a future where missions to the outer planets or even other star systems become feasible due to the enhanced longevity of spacecraft. With self-healing materials, spacecraft could better withstand the rigors of extended space travel, from micrometeoroid impacts to the wear and tear of cosmic radiation. This durability would allow missions to last not just years but potentially decades, enabling a deeper and more sustained presence in space. The Voyager probes, still sending data after over 4 decades, offer a glimpse of what might be possible with even more robust materials. Continuous exploration and data collection would provide an unprecedented wealth of information about the farthest reaches of our solar system and beyond. Furthermore, the adoption of self-healing materials could inspire a pivotal shift in spacecraft design philosophies. Engineers might prioritize modular, adaptable designs over those requiring frequent human intervention, knowing that materials can autonomously address damage. This could lead to the creation of more versatile and self-sufficient spacecraft capable of adjusting to and repairing themselves in the unpredictable environments of space. Such innovations could reduce reliance on Earth-based support and increase the autonomy of both robotic and crewed missions, paving the way for settlement in distant planetary bodies. The implications of these advancements extend beyond individual missions, promising to enhance international cooperation and shared technological progress. As countries and space agencies collaborate to develop and perfect these materials, a global network of shared research and resources could emerge, fostering collaboration rather than competition. This cooperation could lead to the pooling of knowledge and resources, allowing for more ambitious joint missions that leverage the strengths of multiple nations. It would align with the ideals of peaceful exploration, setting a precedent for how humanity approaches other shared global challenges. Beyond the technological and strategic benefits, the societal and scientific implications are equally profound. More durable and resilient spacecraft missions can be more frequent and diverse, allowing for regular observation and experimentation. This can lead to scientific breakthroughs in understanding our universe and discovering new resources, potentially unlocking solutions to Earth's challenges. Plus, the successes and stories from such advanced missions can inspire future generations, instilling a sense of wonder and a renewed commitment to exploration and innovation. Moreover, as we explore potential permanent settlements on the Moon or Mars, self-healing technologies could make these habitats more viable by reducing the maintenance required and increasing safety. The skills and technologies developed could also be repurposed for Earth-based applications, such as infrastructure that adapts and repairs itself, contributing to sustainability and efficiency. Ultimately, the introduction of self-healing materials into space exploration signifies more than just technical progress. It marks a transformative step in how we envision our future in space, encouraging a culture of resilience and innovation. As humanity considers its role within the wider cosmos, these advancements remind us that while the stars may be our destination, the journey is defined by our ingenuity and collaboration. As we wrap up this exploration of self-healing materials, it's fascinating to consider the broader implications of such technology. By pushing the boundaries of what's possible, we not only advance our scientific objectives, but also shape the course of humanity's quest to explore the unknown. The next phase of space exploration promises to be driven by materials as adaptable and resilient as the explorers themselves, heralding a new era where the possibilities are as limitless as the universe. As we draw this exploration of self-healing materials to a close, let's take a moment to reflect on the remarkable insights and advancements we've covered. Throughout this video, we've journeyed through the complexities and promises of self-healing materials, a technological breakthrough that holds the potential to redefine spacecraft durability. From the microscopic wonders of polymers and metals capable of repairing themselves to the exciting applications in satellite systems and long-term missions, these innovations are setting the stage for a new era in space exploration. At the heart of these advancements is a profound shift in how we approach the challenges of space travel. Self-healing materials are more than just a technological upgrade. They represent a paradigm shift towards more resilient, sustainable, and autonomous spacecraft. This resilience not only promises to extend the lifespan of missions, but also to expand the horizons of what's possible as we venture deeper into the cosmos. Imagine future spacecraft that can journey further and last longer, all while maintaining their integrity against the harshest conditions space can offer. But the implications of self-healing materials transcend technical specifications. They align seamlessly with humanity's broader aspirations for space exploration, our desire to explore, to discover, and to push beyond the known into the unknown. As we set our sights on ambitious goals, like setting up permanent bases on the Moon or Mars, the ability to rely on materials that can heal themselves becomes not just an advantage but a necessity. It supports our dream of becoming a multi-planetary species, bridging the gap between aspiration and reality. As Dr. Jane Foster, a leading voice in materials science, aptly puts it, the future of space exploration hinges on our ability to innovate beyond our current limitations, transforming challenges into opportunities for growth and discovery. Her words serve as a powerful reminder of the potential impact these materials can have, not only on our missions but also on our collective vision for humanity's place in the universe. Now we invite you, our viewers, to share your thoughts on this exciting topic. What aspects of self-healing materials intrigue you the most? How do you envision their role in future space exploration? Please let us know in the comments below. We're eager to hear your insights and questions. If you enjoyed this video and want to stay at the forefront of futuristic technologies, be sure to subscribe to our channel. By subscribing, you'll stay updated with the latest in cutting-edge innovations, scientific breakthroughs, and the ongoing journey of exploration and discovery. Thank you for joining us on this exploration of self-healing materials. The universe is vast and unknown, but with continuous innovation, the stars are just a little bit closer. Until next time, keep looking up and dreaming of what lies beyond.